Good day everyone. In this video, we will recap on the first part of Chapter 4, namely on the sinusoid, phasor, impedance, and admittance through some examples. Let us begin. The first part is on sinusoid. Sinusoid is the voltage or current that is in the form of sine wave. For example, in a circuit, the voltage across an element is given by V equals Vm sin omega t. And the current that flows through the element is I equals Im sin omega t plus phi. Vm and Im indicate the peak values of voltage and current, respectively. From the expression, we know that the current leads the voltage by phi radian. When we plot the graph of these two signals, we see that the current, the purple line, is in advance compared to the voltage, the green line. Here, the current reaches its peak value first, followed by the voltage. Therefore, we can say that the current I leads the voltage V by phi radian. Alternatively, we can describe it as the voltage V lags the current I by phi radians. Example 1. In this example, we want to determine the angle relationship between the voltage and current. It is given that the voltage, V, is 3 cosine 3t, and current I is minus 2 sine 3t plus 10 degree. To solve it, first, we need to convert the current signal, so that it is in the form of positive expression. Use trigonometry identity stated here. Add an 180 degrees to the phase of current. Therefore, the current I is 2 sine 3t plus 190 degree ampere. Next, we change the expression of current into a cosine function. This allows us to compare the two signals easily. Again, we use another trigonometric identity. Here, we subtract the angle with 90 degrees. Then, the current I is 2 cosine 3t plus 100 degree ampere. Now, both signals are in cosine form. By comparing these two signals, we see that the current I leads the voltage V by 100 degree. Please remember that this comparison is applicable only for the same omega. Example A2. We are required to express the voltage signal in this form. Vm cosine omega t plus phi. The voltage is 3 cosine 4t plus 4 sine 4t volts. So how are we going to solve this? In this question, the sine and cosine functions have the same omega value, that is 4 radian per second. Therefore, we can solve it by using the trigonometry function, as shown here. Draw a right-angled triangle to visualize it. The peak value, Vm, is the square root of sum of a square and b square, while phi is the arctangent of a and b. Substitute the values accordingly into the formulae, we get Vm equals 5 and phi equals 53.1 degree. Therefore, voltage V is 5 cosine 4t minus 53.1 degree volts. Now, it is a recap on phasor. Phasor is a representation of a sinusoid in the form of complex number, indicating the sinusoid's magnitude and phase. Phasor is actually the way we represent the sinusoid in the frequency domain. We can write phasor in several ways, such as the exponential form, the polar form, or the rectangular form. For example, the sinusoid of V equals Vm cosine omega t plus phi. It can be written this way. That is in the exponential form, or in the polar form, or in the rectangular form. Usually, phasor is used to find the steady-state signal of a linear circuit. We can apply phasor concept when all the independent sources are sinusoids, and they are of the same frequency. In the case when there are two sinusoids of different omega values on the circuit, the superposition principle is applied. The effect of each sinusoid can be analyzed independently using phasor. Example B1. Write down the phasor of the current I. If I equals 4 times cosine omega t minus 80 degree amperes, and I equals 8 sine omega t minus 20 degree amperes. The answer for part A can be obtained easily. This is because the current I is the cosine function. Don't forget, the current I must be written in capital letter. This is magnitude 4 and phase is -80. For part B, first we convert the current into cosine function by subtracting 90 degree from its angle. Hence, I equals 8 times cosine omega t minus 110 degree amperes. Now, we can express it in phasor, that its magnitude equals 8, and phase is minus 110 degree. Again, the current I must be written in capital letter and bold. Example B2. Here, the voltages are in phasor. We need to determine the steady-state values of the voltages. In question A, the phasor voltage is in polar form, while in question B, it is in the rectangular form. The answer for part A is very straightforward. We just convert the voltage from the frequency domain into time domain. Use a small letter to distinguish Vt from its phasor form. Therefore, Vt equals 10 times cosine omega t plus 60 degree volts. The omega is used to represent the angular frequency, as its value is not provided in this question. In part B, we need to change the phasor voltage from rectangular form into polar form. Its magnitude is the square root of the sum of real value square and the imaginary value square, while the phase is the arctangent of the imaginary value over real value. Once it is done, we can convert it into a time domain signal. Vt equals 109.7 times cosine omega t plus 43.2 degree volts. On this part, we do some revision on the phasor relationship for a resistor, an inductor and a capacitor. Phasor is the transformation from time domain to the frequency domain. With this transformation, the mathematical part of the equations that describing the circuit can be simplified. It is because in the time domain, we will be dealing with the differential equations. Whereas in frequency domain, which is phasor, the equations are the algebraic form. Hence, it will not involve the differential or integral operation. These diagrams show the circuit in time domain together with the equations that relate the current and voltage of these passive elements. For capacitor and inductor, the IV relationship is in differential equation form. To solve for any circuit that consists of these elements will require us to do some differentiation or integration if we solve it in time domain. However, if we solve it in frequency domain, which is phasor, it will only involve the algebraic operation. The diagrams at the bottom are the same circuit, but they are in frequency domain. We see that the equation relating the voltage and current of the inductor is now simplified. It is not the differential equation, but just an algebraic equation. Similarly, for the capacitor. What is an impedance? The impedance of an element is a ratio of phasor voltage to phasor current. The unit is ohm. If a phasor voltage of an element is V equals Vm magnitude and phi angle, while its phasor current I is Im magnitude and beta angle, the impedance is simply V over I. Therefore, its magnitude is Vm divided with Im, while its phase is phi minus beta. The impedance is similar to the resistance of a resistive circuit in time domain. It also means that the Ohm's law is applicable when we solve any circuit problem using phasor concept. At the same time, please note that impedance is not a phasor. Next is about the admittance. Admittance is defined as a ratio of phasor current to phasor voltage. It is the reciprocal of impedance. The unit for admittance is Siemens, or S, in capital letter. It is similar to the conductance in the resistive circuit. These are the same diagrams that you have seen in the previous part. What I want to highlight is that, by using the impedance concept, we can easily solve a circuit problem when a sinusoidal voltage source or current source is being supplied to the circuit. The complexity of the mathematical part has been reduced tremendously, as it is in the form of complex algebra. Example CE1. In this example, we want to calculate the impedance and admittance for a 10 mH inductor when the omega is 1000 radian per second. This is a very straightforward problem. We just need to apply the formulae. For the impedance, ZL equals J times omega L. Substitute the values, we get the impedance. ZL equals J10 ohms. Next, for the admittance, it is the reciprocal of impedance. Therefore, YL is 1 over J omega L. Substitute the values and multiply top and bottom with J, it gives us YL equals negative 0.1 J Simon. This is because J square equals -1. Or, we can leave the answer in the polar form, as shown down here. Therefore, we find the magnitude and phase instead. Hence, YL equals magnitude 0.1 and phase -90 degree, unit in Simon. Example C2. This the final example of this video. For a given circuit in figure C2, we need to calculate the total impedance and admittance, as seen from A-B terminals. The angular frequency is 1000 radian per second. The circuit comprises of capacitors arranged in both series and parallel connections. Therefore, first, we find the total capacitance, as seen from terminals A-B. From the series connection of 3 mF, 1.5 mF, and 1 mF capacitors, we get C sub-series is 1/2 mF. Then, the total capacitance is the equivalent capacitance of 3 parallel capacitors, the 2 mF, 0.2 mF and C sub-series. Hence, C subtotal equals 3 mF. Once we have calculated the value of C subtotal, we can apply the formula to find the impedance, as seen from terminals A-B, that is Z equals 1 over J omega C subtotal. Substitute the values, we get Z equals -J 1/3 ohms. Finally, we can find the admittance, as seen from terminals A-B. The admittance formula for a capacitor is given by Y equals J omega C subtotal. Key in the values into the equation, we get Y equals J3 Simons. In this video, we have gone through some examples on the sinusoid, phasor, impedance, and admittance. In part 2, we will see some examples on circuit analysis using phasor concept. That's all for this video. Thank you for watching.